Let us move on to the next important load, which is ice load. Ice loads are generally dominant in Arctic region. Prediction of ice loads has lot of uncertainties. Ice actually exists in different forms like level ice, broken ice, ice ridges and icebergs. Ice can result in various effects. Ice loads can cause various effects on members. It can cause creep, can cause buckling, it can cause spalling, and the failure can also be due to crushing. These are all different kinds of failures which can be caused by ice on members. More interestingly, ice loads also vary both in space and time. So, ice loads can be classified as below. 1, total ice load, otherwise called as global load. 2, local load, otherwise called as pressure. Interestingly, the global loads affect overall motion and stability of the structure, whereas the local loads affect members at local points, or let us say critical sections. So, the most important factor in ice load estimate is the number of interactions between the member and ice. Interestingly, the current international codes include equations for estimating ice load as static ice loads. It is important to know that ice loads also depend on shape of the structure which it is encountering. Studies show that ice loads on conical structures like pyramids are lesser than cylindrical structures. So, that is given by a good reference, Sanderson 1988. The main reason for this reduction is due to the fact that the well designed conical geometry can alter the failure mode of the structure caused by ice from crushing to bending. That is the reason. So, ice given again by a ice force spectrum on a narrow conical structure This is given by the following equation: A f bar square t bar minus delta divided by f r exponential minus b by t bar alpha and f beta. Equation 1. In the above equation, A and B are constants whose values are A is 10 and B is taken as 5.47. T bar is L B by V, which is called ice period. L B is called ice breaking length. Typically, it is between 4 to 10. F bar 0 is called force amplitude on the structural member. The ice breaking length is given by K into H, where K is the ratio of ice thickness to ice length, where this lies between 4 to 10, not this value. F is the frequency, which is the variable in the spectrum, and V is the ice velocity. The constants alpha is 0.64, beta is 0.64, and F 0 is given by C sigma f h square d by L c to the power 0.34, where C is again a constant, which is 3.7. Sigma f is ice breaking strength, which is 0.7 megapascal. H is the ice thickness, d is the diameter of the ice cone, and L c is the characteristic length. So, the equations, the power gamma and del are respectively 3.5 and 2.5. The characteristic length L c is further given by E h cube by 12 g rho w raised to the power 0.25, where E is ice elastic modulus, which is given by 0.5 gigapascal, and rho w is density of sea water. A typical ice spectrum, which can be plotted, is looked into the figure here, and we have given the program to plot the ice spectrum on a narrow conical structure. The plot shows the spectral density versus frequency. The constants, as I said, are already given in the equation A 10, B 5.47, and other constants are named as per the programming variables as alpha, beta, gamma and delta. So, now the plot is shown on the right hand side, whereas the coding required to plot the ice spectrum is given on the left hand side of the screen. So, you can use this coding directly to get the ice spectrum for Bohai Gulf as you see here. The next kind of loading is earthquake load. We understand that offshore structures which are stiff and connected, that is fixed to the seabed, will undergo or will experience earthquake loads directly. Okay. However, complaint structures like TLP, will also experience earthquake loads. Let us see how. This is a superstructure of the TLP connected to the seabed using tendons. The seabed experiences earthquake loads. Earthquake loads cause ground displacement, that is displacement of the seabed. This induces change in T0. This change in T0 alters buoyancy and weight and stiffness in the TLP. Therefore, earthquake loads have indirect effect on complaint structures. We all know from the literature that earthquake acceleration exhibits random characteristic. This is due to nature of the mechanism causing earthquake. 2. It can be due to wave propagation. It can be also due to reflection, and further can be due to deflection. What are the consequences of earthquakes on offshore structures? 1. It can cause inertia force due to the acceleration. It can result in a damping force due to motion of water particle. So, as I said, in complaint structures like TLP, the T0 varies. This causes dynamic tension variation. So, this variation is given by a factor of the axial stiffness, which is x t minus x g of t, where x t is the instantaneous response vector of TLP, and x g of t is ground displacement vector. One can quickly look at this vector. It is going to have the effect in surge degree, no effect in sway. It will have effect in heave degree, no effect in roll, pitch and yaw. So, I should say now that x 1 of g is actually horizontal ground displacement and x 3 of g is vertical ground displacement. So, earthquake causes displacement and the ground motion which is caused by earthquakes is simulated by Kanai-Tajimi ground spectrum. The one sided power spectral density function is given by S x double dot g of omega is omega g to the power 4 plus 4 zeta g square omega g square omega square by omega g square minus omega square the whole square plus 4 zeta g square omega g square of S 0, where S 0 is called intensity of excitation, which is given by 2 zeta g sigma g square by pi omega g 1 plus 4 zeta g square. Omega g is natural frequency of the ground motion, zeta g is damping of the ground motion, and sigma g square is variance of the ground motion. So, these three are important parameters of Kanai-Tajimi spectrum. So, Kanai-Tajimi spectrum is a 3 parameter spectrum. What would be the consequence of this? The consequence of this on let us say compliant structures. Like TLP could be, it results in dynamic tension variation in T0, and this variation can be as high as 65% causing pull out. It affects rigid degrees of freedom like heave, which is quite dangerous because it can challenge the safety of the platform. This ultimately also results in loss of functional value of the platform. So, detailed results can be seen from the following textbooks. Advanced Marine Structures, authored by me, published by CRC Press. There is one more book which also discusses the behavior, again authored by me, dynamic analysis and design of offshore structures edition 2, Springer, Singapore. So, friends, for different damping ratio, the typical Kanai-Tajimi ground spectrum looks like this as you see on the screen now. Let us see the summary what we learned in this lecture. We did one more numerical to understand the wind loads on superstructure of the platform. We have used API code to compute the wind velocity. We have learned how to estimate ice loads. We have seen ice spectrum. We have also learned how to calculate earthquake loads. We have learned Kanai-Tajimi spectrum. So far we have learned wave loads, wind loads, ice loads, earthquake loads, including the computer program to calculate them, solving example problem to understand them. I hope you followed these lectures and you will be able to write these programs on your own and check the results and compare the answers what we have in the screen here. Thank you very much.